There we go.
Thanks. All right, so, sorry, I forgot to. Okay, so just a quick reminder of representation theory, just to anticipate what we should see related to particle production. Well, so the first point that I made is that self-interactions peak around the equilateral. Okay, so for sigma, a scalar, the mass, so up to 0 is forbidden. Then, now let me be a little bit more precise. So there is a particular value that I think in terms of representation theory is part of the complementary series, but the mode function is very simple. This is the conformally coupled scalar. Meaning that the mode function is just a plane wave, essentially. Then this is the divide, is 3/2 of h. So this is the complementary series, meaning that at late times, the two-point function decays like a power law. And this is the principal series, from which point you have oscillations in the two-point function at late times. So just to drive this point, if I plot the two-point function of sigma, the quantum field as a function of conformal time, then it will oscillate at 1/k. It transits into this power law behavior. For the massless field, let me take a couple of colors. So for the massless field, it goes to a constant. Then for complementary series fields, they decay like power laws. And then for principal series fields, the two-point function follows some sort of envelope, but it oscillates. Okay. And well, okay, this is a cartoon, so I just offset a bit the value just to emphasize that, okay, the frequency of oscillation is mass dependent, but it's also important to emphasize that the overall value starts decreasing with the mass. There's some Boltzmann suppression, in other words. So there's the sigma also goes like e to the minus m over h for m bigger than 3/2 h. Okay. Again, this m is with quotes. It's some square root of m squared, blah, blah, blah. In such a way that if the mass is much heavier than Hubble, there's Boltzmann suppression. There is production, but it becomes inefficient very fast. So you have a chance of seeing something as long as the mass is of sigma is between 0 and number order 1 Hubble. Which number order 1 is, as a model builder, it's your task. But, for example, maybe if you work very hard, 50 order Hubble, but not 1,000 Hubble, okay? not 10,000 Hubble. But order Hubble, you will for sure be able to see something, or at least to generate some imprints.
Sorry, one question. Maybe I missed it or I don't understand. What happens when you have equal to 3/2 h? Is it exactly equal to 3/2 h? Order between the...
Yeah, then it's a power law, and then well, the wavelength of oscillation is infinite if you wish, and then yeah, then the heavier it is, the more oscillations it will have. So you go from power law to like then you increase the mass a little bit, then it starts oscillating very, very slowly and very heavy. Right?
Thank you.
Yeah. Okay. Now let's talk about spin. Someone asked about this yesterday. I call spin J. Let's hope I'm consistent. Spin greater than 2 is spin equals 1, the story doesn't change much. Spin greater than or equal to 2, the story becomes interesting in the sitter. Let me describe what happens for J equals 2. So then there's the forbidden region, and then there's the graviton. It's okay, mass equals 0. Then the complementary series and the principal series are again divided at 3/2 h. So this is the principal. But now there is a surprise. The complementary series ends at square root 2h. And actually, this is all forbidden. Okay. So this is a peculiarity of the sitter space. Sorry, I'll lower the board in a second. Just focus here for now. And another way that makes the story interesting is that, you know, a massive field, a massive spinning field has 2j plus 1 degrees of freedom, which is in this case 5. The graviton has 2 degrees of freedom. This guy here actually is special at the end of the complementary series. There is a, if you look at the quadratic Lagrangian, there is a new gauge symmetry, but it's a scalar gauge symmetry. It removes 1 degree of freedom, so it has 4 degrees of freedom. It's called the partially massless graviton. It's interesting, it propagates 4 degrees of freedom. The mass has to be tuned to the cosmological constant, so it would be interesting if there was an interacting theory of such an object. As far as we know, there isn't. There is no super robust no-go yet, but people have tried, and it turns out to be hard, if not impossible, to build an interacting theory of such object. And the story repeats. So as you go to higher spin, there will be a principal and complementary series, and at the edge of the complementary series, you lose 1 degree of freedom. But then to go all the way to mass equals 0, there will start being islands. So there will be like specific points in which you lose pairs of degrees of freedom. So these are called partially massless fields. Just to show you another example. For this, I haven't copied the right numbers, but just to contrast, just to highlight. These representations in ADS are all non-unitary, so that's, if you come from ADS CFT, it might be surprising, but they're unitary, completely fine. So for example, J equals 4. There will be a continuum. there will be, the complementary series, the principal series, the complementary series. You will start with, there will be the edge of the complementary series. Everyone here will have 2j plus 1, which is 9 degrees of freedom. Then here you have 8. Then mass equals 0. There's 2 degrees of freedom. And now there will be 2 islands. 6 and 4 degrees of freedom. Okay? And then here it's all forbidden.
Actually, one other question, because I'm mostly familiar for the S3 representation. Usually, when it excludes, it's because of there's some unitarity bound and there's violated and so on. Here, how do you exclude some regions? So also
if you one way to look at it is if you look at the quadratic action, and then you do like Stuckelberg just to separate the various helicity modes, you will see that the kinetic term controls, the mass term controls the kinetic term of lower helicity modes, and you see that some of them become ghost-like once you go beyond this bound. And then when you hit these points here, some of these ghosts disappear. They have 0 kinetic terms. So that's why you have a unitary representation there. Another way of looking at it more on shell is you look at the late time 2-point function, and you do a helicity decomposition of the late time 2-point function. Then you see that you will have coefficients in front of the 2-point function that are negative. So this is described. This point of view is described in the paper of Arcani, Hamed, and Maldacena, Cosmological Collider Physics. Just so you know. So this is correct, I hope. This is only valid for J. For scalars, the story is different. But as long as J is non-zero, this is what happens. J minus.
Is it always pairs of helicities always get reduced? So it's always reduced by 2?
I think so, yeah.
And does it keep getting reduced by 2 all the way down to 2 degrees of freedom, so there are as many number of points?
That's right. That's right, yeah. Yeah, you will become clear once I write the formula for these special representations. So this will be the principal series. Then this is the complementary. And then so this is called the depth. This quantum number people call the depth of the partially massless field, and then the depth can acquire any value from 0 all the way to J minus 1. Okay, so when you put in J minus 1, it's 0, and then when you put 0, you get the edge of the complementary series. So what happens if you're familiar with ADS CFT, so the dual of a spinning field, of a massless spinning field, so let's take a spinning field H mu1 mu s, mu j, sorry, it's massless, then the dual operator is some conserved current, J mu1 mu j, such a way that if you take the divergence, it vanishes. Then a partially massless field, mu1 mu, unfortunately everything looks similar here, mu j, such that now the associated current mu1, you need to take S or whatever T divergences for it to vanish. You need to take multiple divergences. So that's where the partial masslessness comes from. So in particular, the PM graviton will be such that the stress tensor is doubly conserved. So it only removes 1 degree of freedom instead of a vector. So that's how you do the counting to see that you reduce 2 at a time. Okay. So, yeah, this is more of a curiosity. I won't focus too much on partially massless fields, but I just wanted you to know.
Are these all the unitary representations of SO?
Integer spin, yes. But there's an analogous story for fermions, but I'm not describing them. Yeah. I don't think there are analogs of continuous representations. So I think that's all there is. In higher dimensions, there's something called the exceptional series and so on, but okay, I'm not an expert, so it's being classified. There are papers. This guy Zimo Sun that go through it in a lot of detail in these dimensions. Yeah. I don't think he's done fermions, but I think he completely classified. Ah, okay. So there you go. So if you look at his papers, then you'll find the general classification of ERAPs. Okay, so let me say a couple of things about detection. For that, let me write the formula for the 3-point function of density fluctuations. There's a nice way of parameterizing it. So that will be translation invariance. This soaks up the scale dimension of the 3-point function. And so this is dimensionless. We call the shape function. It's not terribly important, but just so I write some precise formulas for the scaling. So around the equilateral limit, and then the overall size we call FNL. So it means that in the equilateral limits, we normalize B to be order 1. It's like 5/18. It doesn't matter. It's just some number that some convention in such a way that this is order 1, and then we measure the overall strength of the signal by this parameter FNL. Okay? So currently bounds on FNL depend on the shape function, depend on B, and let's say that FNL right now is roughly less than order 100. Okay, it's kind of pessimistic actually. It's a little bit better for certain shapes. It's much better, but yeah, just to give you a proxy. So you might say, "Wow, I mean, these people suck at experiments. Order 100. But that's pretty damn Gaussian because if you compare with the size of the 2-point function to the power 3/2, then and you plug in the AS to the power spectrum to the right power, then the 3-point function normalized by the 2-point function is less than I think 10 to the minus 2 or 10 to the minus 3. I might have a plot. Yeah, I think it's like 10 to the minus 2 or 10. So it's very Gaussian, but we expect some level of weak non-Gaussianity. All right. And so now let me show you how we will do spectroscopy. How we will be able to detect new states by looking at the shape function. And then for that, we must go to the squeezed limit. So we must look at squashed triangles. So it's this blackboard here.
Excuse me.
Yes.
So you said there is a classification for fermionic representations in any dimension?
Apparently, yes. Don't quote me, but apparently it's in the papers of Zimo's son. Yeah.
You discussed that if for the particular case of SO1,2, there are no parity odds of fermionic representations in the complementary series, but there are in the principal series.
For arbitrary dimension?
That I don't remember. I remember that for SO1,2 is discussed in detail. I don't know if it discusses the dimensions in
I thought it's generally in the principal series, in all dimensions. But it does not discuss.
So principal series does not have massless fields. So
So it lectures 4 or 5. I'm looking at the focus I have.
So if you just write a self-interaction, it goes like, remember I said that local interactions don't leave a lot of signal in the squeeze limit, so it decays like a second power of K1 over K3. In fact, for self-interactions, you can write, for the shape function, you can write a power series in K1 over K3 to the integers with AN. And only starting at A2, you have theory-dependent data. You will depend on the particular type of self-interaction that you put for, oh, now I removed the, you will depend on particular type of interaction vertex that you dial here. At level 0 and 1, it's all fixed by soft limits. So there are soft limits for this 3-point function. And the coefficients at order 0 and 1 are fixed by the size of the 2-point function. It's like, they're called, the 0th order one was first discussed by Maldacena, and the first order one was discussed by a group at ICTP in Trieste. And we know that there are infinitely many soft limits, but beyond the leading and subleading, they just relate different 3-point functions. So anyway, so there is a whole story of soft limits here also. But so you see that there is non-analyticity. There will be a power in between 0 and 3/2 for a complementary series. And starting from the principal series, there will be oscillations. So this is cool. There is a new feature that comes from oscillations. Unfortunately, it's sort of logarithmic. well, this is the mass in quotes. It's like the square root story. So it's hard to detect because you need a lot of hierarchy between the long and short modes. And there will be some phase that is also mass dependent. Some phase that depend on M. So this is for scalars. And for spin, so you'll have B for spin 0, K1, K2, K3, times Legendre polynomial, J, that will depend on cosine of theta. Let's see if where theta is the angle between the small K1 leg and the large K3 leg. So this is theta here. So you go to the squeezed limit. You go to the squeezed limit, you measure the 2-point function, and then as I start dialing an angle, you can think of the two particles as a polarimeter. So this particle here, so there's K1, there's the new state, and then K2 and K3, as I dial an angle, they act as a polarimeter. So that's why I see modulation of the 2-point function of the new state. Okay? So that's how you do spectroscopy. You go to the squeeze limits, and that's it. I have some plots here, but I hope it's clear. The appearance of the Legendre polynomial technically comes from contracting the polarization vector of this spinning field. I only exchange the longitudinal part of the spinning field because it's linearly mixing with a scalar. But then I have to contract, I have to soak up the polarization vector for the longitudinal part. I have to contract it with the external momenta. So that's how I produce the Legendre polynomial, technically. Okay? All right, so how do you calculate? So this is all phenomenological. How do you calculate in practice the shape of non-Gaussianity? So there are two different things you can do. So let me describe them. I will probably use them interchangeably, but if you do the careful computation, you should make sure that you know which one you're performing. Okay. So I call this computing non-Gaussianity. So two different things you can do. One is bulk perturbation theory. And here you only control the initial states of the universe. So it's unlike Feynman perturbation theory, you control the in states but not the out states. So they are called in correlators or in formalism, Schwinger-Keldysh formalism. There are many names, in correlators. And there are many reviews for this. You can look at the review by Xingang Chen from 2010. Steven Weinberg, when he wrote a famous paper on cosmological correlators from 2005, he reviews this in an appendix. And so the idea is that I control the initial state of the universe and I want to compute the expectation value in a given theory for given particle contents and self-interactions. 3-point function of the density perturbations. So unlike Feynman perturbation theory, so in Feynman perturbation theory, so you compute this at fixed time. So you control the initial states. Let's say you evolve, you start maybe from the free vacuum. Okay. Then you do some I-epsilon prescription, you go off into the imaginary time axis, but then you eventually get into the real axis. Then you go all the way to the point of insertion of the operators, eta naught. You insert the operators, zeta, zeta, zeta. But now you don't continue, right? In Feynman perturbation theory, when you compute a connected, you introduce the Dyson operator, right? So you have expectation value, time ordered, exponential, integral Hamiltonian, phi, phi, phi. So in particular, you insert your phi's at different times, phi 1, phi 2, phi 3, and you carry on phi 1, phi 2. All the way from minus to plus infinity. Here we go back. Okay? Because you need to generate the bra of the interacting vacuum at early times. So there is a branch that moves you forward in time and a branch that moves you backwards in time. And actually the causality of the correlators is more manifest in this picture. Here it's a little bit funnier because it seems that to compute a correlation function you need to know about the future. But as we know, well, we're still trying to understand all the consequences of causality, right? But the picture is causal. Here it's slightly different. So technically you have to evolve, you have to introduce the Hamiltonian that moves you forwards in time, the Hamiltonian that moves you backwards in time. So perturbation theory is a little bit different. So this is one way. So this would be in-out. So it's not in-out. We're going to do in-in. Another thing you could do, which is closer to what we do in ADS CFT, is to compute the Schrodinger wave function. Instead of in the Heisenberg picture computing expectation values of operators, you compute the Schrodinger wave function and you use the Born rule. So this is the method of this is alternative. It's the wave function of the universe. Here, what you do is, so time goes forward like this. You have your eta naught, and you prescribe late time Dirichlet type of boundary conditions. So you specify the field, the profile of zeta at late times. And then you impose that the field zeta is regular or satisfy vacuum boundary conditions, that zeta of k, eta goes to minus infinity, goes like e to the I k eta. Okay? It's a single, for each partial wave it behaves like single exponential at early times. Okay? It's like when you solve things in ADS CFT, you impose bulk regularity as you dive into the bulk. And then you compute the wave function of the universe as a function of the profile. Zeta of x at time h naught. So this is some highbrow path integral, blah, 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 in quantum gravity. Of course, in practice, the only thing you do is you compute the classical action, the action on the classical saddle. But then you need to know the interacting Lagrangian to get the cubic vertex. So this is the wave function. It's a function of a C number, the scalar profile at late times, and then to compute the expectation value of zeta k1, k2, k3, you apply the Born rule. Because you're working in some weakly coupled theory, you just compute this to leading order in the semi-classical approximation, and there's a simple formula that will give you, in terms of the wave function coefficients, it will give you the expectation value. So the goal is to find the expectation value. You can do it in the Heisenberg or in the Schrodinger picture. Some things are simpler in one picture, some things are simpler in the other. If you really want to do bulk perturbation theory, you need to solve the Hamiltonian dynamics. If you want to do wave function of the universe, you need to integrate the bulk vertices over time. Okay? In both cases, the computation is hard because certain aspects are simpler in one approach versus the other. Questions?
Can I just ask, in whatever formulation of distributed holography that we have, is it this wave function of the universe that is interpreted as some CFT partition?
Yeah. So the proposal of Maldacena, for example, so ds CFT, the idea would be that the wave function of the universe, so in this case it would be full-blown quantum gravity, so it must satisfy some Wheeler-DeWitt equation and so on. But it will depend on some data, some sources, zeta of x, maybe the Graviton, etc. This would be computed by partition function with some classical sources of some whatever object. I mean, one criticism of this proposal is that say you compute it, it's highly non-Gaussian, then you still must apply the Born rule. Then you need to talk about integrating over metrics and so on. But okay, you trade, I think it's still progress because you trade, now time evolution should be emergent and you must integrate over Euclidean 3 metrics. I think it's progress, but some people criticize this proposal, or I think it's fair to point out that it's not entirely satisfactory, if you wish, because then you must still make sense of this formula. But I say it's progress because at least you should understand, without applying the Born rule, you should understand how time evolution is emerging from this picture.
So the CFT lives on the eta naught slice?
Yeah, as in holography, you forget about this, you think about another problem, and the other problem would be the CFT put in some curved Euclidean background, and the curved Euclidean background has the same geometry as the eta naught slice here.
Sorry, just one very basic question, a stupid one. Why are you sure it's a CFT? The dual one.
We don't know that it's a CFT. What we do know is that the kinematics of the Sitter space implies some isometries or some ward identities for the expectation values at eta naught. And these ward identities are the same ward identities of the same kinematical constraints of conformal field theories. Now, we don't know about operator products expansion. Clearly, the conformal dimensions that are allowed are different because the ERAPs have these oscillatory features that they don't exist. So you should be allowing yourself to talk about complex conformal dimensions. Clearly, well, here we control Dirichlet boundary conditions, so maybe it still makes sense to talk about source and response. But in the true expectation values, they're both playing together. It's the growing and the decaying mode. And for oscillations, they're on equal footing. While in ADS-CFT, you have a source and a response, and they're separate things, right? So the
Including CFT, having complex dimensions is not
right.
not really crazy.
No, it's not. I think the puzzle is, so in ADS-CFT, there's a very good reason why the CFT should be, even in Euclidean signature, should be reflection positive. Because if you Wick rotate, then the boundary time asymptote is related to the asymptotic limit of the killing vector in asymptotically ADS spaces. So bulk unitarity and boundary unitarity are very closely related. Well, here, there is bulk unitary time evolution, but then there's some object here at late times. So the bulk unitarity is encoded in some property of these objects that now we think is related to some spectral positivity and so on, but it's not just naive CFT unitarity constraints.
And this unitarity, fact that it looks like non-unitary, the dual theory or whatever it is it related also to this production that happens because of curvature expansion, particle production by curvature expansion?
Right. If you wish, that's one aspect of it. But just one very simple-minded thing is that there's complex conformal dimensions, which you typically wouldn't allow.
Yeah, but in the bulk, I mean, the interpretation of this, just like
these are unitary representations in the bulk, so there is nothing very special. By the way, I noticed that it's 3 halves here, not 1/2. Sorry. I think everything is unitary and normal in the bulk, but then it's reflected as some unusual properties in these boundary objects. We call it CFT because it has the same kinematical constraints of a CFT. But the rules of the game of these objects are different. Okay. Yeah, maybe one... There are 2 goals, if you wish, of this cosmological bootstrap. One is the cosmology goal. Let's classify shapes of non-Gaussianity, understand the initial conditions of the universe, and so on. And the other is maybe if we have enough data, we can learn the rules of the game of some holographic dual. So they run in parallel. So how do you go about actually doing the computation? Maybe I'll just sketch. I hope my hope is just to convince you that it's hard, not to teach you how to do the computation, because we're going to try to do it from a different perspective. So computing via bulk perturbation theory is hard. To be completely fair, some things are simple. So if I have self-interactions, things like that, it's not so bad. You have only one time integral to do. You have a single time integral of some mode functions and so on, like bulk to boundary propagators, if you wish, times some, so there will be some external mode functions. I'm being very, very, very cartoonish here, okay? You integrate from -infinity to 0. There's an I-epsilon prescription. So this generates the cat. You need to add another term that will generate the bra. That will be e to the minus ik1 e to the minus. There will be some measure, eta to a certain power. There will be some vertex function that will depend on the momenta, and eta, and so on. Maybe complex conjugates here. So this is not so bad. You can do the integral, you get some formula. That's fine. Now there is, but actually historically the first computation that did this solved a harder problem, which is closely related to the problem that we're actually interested in to understand how to do spectroscopy. So for self-interaction is not so bad, but what about this diagram here? Now, this was first done by Maldacena for the case of graviton exchange. Okay? So here you exchange the graviton. It doesn't look so bad because you see there is a angular momentum conservation. So all you really exchange is the longitudinal part of the graviton, or the Newtonian potential. So all you're really calculating is the attraction of the three scalar particles to each other due to Newtonian dynamics. Okay? So it doesn't look so bad, but it's a very painful calculation. One reason why it's hard is because you need to solve these constraint equations, plug them back in, but then you also are in this slow roll approximation. And if you just follow your nose, you get 0. If you do the leading order computation, you get 0. You do the subleading order computation, you get 0 again. So the cubic action is actually, if you just follow naively, try to write down the action in the zeta gauge, it doesn't give you the right leading order answer in slow roll. So the cubic action, so in the end, because it's just the Coulomb interaction, it's equivalent to having some effective interaction vertex. There's some effective interaction vertex. It will be non-local because I'm integrating out the Coulomb potential, but it will be non-local in space. It won't be non-local in time. So that's fine. But then if you just write down the cubic action naively, it will be order epsilon to the 0, which it's okay, but then you compute the resulting 3-point function, you find that it's 0. So it's not capturing the true effect. So you need to work pretty hard, blah, blah, blah. I'll spare you. Okay? It's actually order epsilon squared. So you need to massage, you need to redefine, so you need to find zeta c, which is a function of zeta, that will really capture the leading order effect. And then you get something that is order epsilon squared, which is good news because it's the smallness of epsilon that makes the computation reliable. And there's subleading in epsilon stuff that you throw away. And then the cubic vertex looks like this. Zeta dot c squared inverse Laplacian zeta dot c. Okay? So now that I wrote the answer, you're like, that's easy. Then I just plug in the formula and I go home. But to get there, if you go home and try to reproduce this, it'll probably take you, even with guidance of the paper, it'll take you a couple of days to do it. This is just to exchange the Newtonian potential. So to actually exchange the full graviton, if you're interested in, say, the 4-point function, and you do full graviton exchange, this was done some heroic computation by, among others, Filippo Vernizzi, and it's it's just too hard. There should be a simpler way of. It's because you're trying. It's a gauge theory because it's gravity. Where you have to solve all these constraint equations. You only want to propagate the physical degrees of freedom. It's just too complicated. And then when you look at the final answer, it's a rational function. So, interesting. For generic massive exchange, so this is a nice property of the fact that everyone here is massless. So it's a massless scalar, massless graviton, and so on. If you try to repeat this exercise, say we're interested in a generic massive spinning exchange, then we didn't even know how to begin in terms of writing an analytic formula. You could produce a plot, you would see that you measure the two-point function, you'd see features and so on. But to actually compute the full shape function is just too hard. So can we do better? The procedure is not scalable. It's too complicated. Well, that's where the idea of this cosmological bootstrap comes. Okay. So now we're on item 3. Okay. So now we're in 2018, so we're getting there. Tomorrow I hope I get to 2022. So the problem is to solve reliably and efficiently for the shapes of non-Gaussian. Okay, so we would like, for example, to understand how to compute this diagram for generic sigma, for generic mass and generic spin. Is there a reliable way of doing this without like having to go back to the drawing board computing? Now you have nested time integrals. You have two integrals to do and blah blah blah. Okay, is there something easier? So now the first thing to do in this, so we're going to take inspiration both from ADS CFT or holography plus S matrix or scattering amplitude technology. Okay. So the first thing to do is to try to trade this for a problem in de Sitter. So this is done in inflation. Maybe it's closely related, which I already mentioned to you, to a problem in de Sitter. This is what we tried a few years ago. Now we can actually solve for, the technology is actually applicable straight to this problem, but it's just, I think, pedagogically better to discuss this example because there's a lot of symmetry. So you trade this in de Sitter for computing this 4-point function in de Sitter, and you would like to compute the 4-point function for generic massive exchange. So it's clear that you should look at the 4-point function because the 3-point function is unique in de Sitter. Is unique, and it's just coming from phi cubed interaction. Anything else will generate the same shape, and actually it's not interesting because it has a kind of an infrared divergence because the scalar field is very light, and this is breaking shift symmetry. So the zero mode of the scalar field is leaving strong fluctuations at late times. And it has some logarithmic form. It's not very different from the equilateral shape of non-Gaussianity. You can compute it. It's being computed by various people many times. But the point is that in any case, it's unique. Okay, so you calculate it once, and then you're done. The richness is coming really from the de Sitter 4-point functions. So in the de Sitter 4-point function story, we'll break up the problem into two simpler problems. There are two easier problems, or at least we, instead of going straight for the exchange, we first do something easier. So in our quest to classify possible de Sitter 4-point functions, we first start with self-interactions. So contact interactions. And then we're going to do scalar exchange. So this has generic mass, but spin 0. So scalar. And then symmetry will come to the rescue. So I claim that if you understand the dynamics of this diagram, then there's so much symmetry in the game that you understand all other diagrams at 4 points. Meaning that you can apply some differential operator to the answer and you generate spinning exchange. So you don't need to worry about like, well, how we're going to make it for a higher spin and so on. Okay? So if we understand dynamically this and this diagram, then everything else that is more complicated, at least at 4 points, follows from symmetry. And at 3 level, okay? I'm not going to say anything about beyond 3 level. Let me give you some inspiration for why we expect that we can classify completely 3-level diagrams in de Sitter. It comes from flat space, okay? And then I have 5 minutes, is that right? Yeah, so then I'll wrap up. Okay, so inspiration. Two to two, 3-level flat space scattering. So say you're interested in the scattering of 4, let's make them identical scalars at 3 level. As a model builder, you have the whole universe at your disposal. So you can build all sorts of self-interactions and add in all sorts of new states. But then the theory must be local, unitary, Lorentz Poincare invariant. So actually this problem is, even though the space of Lagrangians is infinite, you can write down a formula that depends on infinitely many parameters, but you can just write down the formula for any possible scattering amplitude, despite the fact that you can clearly not write all possible Lagrangians. So the scattering amplitude, so first of all, because of symmetry, this is so hardwired that we often forget that it's powerful. Naively, the kinematical data is 12-dimensional. I need to specify the 3 momenta of all particles. There are 12 pieces of data I need to specify. But we have 10 isometries. So therefore, there are only 2 kinematical invariants. So physics only depends on 2 variables, the Mandelstam's S and T. So this is a consequence of Poincare symmetry. Now, there are 2 possibilities. They can self-interact. And locality tells me that if they self-interact, then at low energies, the signal must disappear. Therefore, I can write down polynomials. And maybe I was color coding. This is related to locality of the interaction vertex. And then I can go and fit this to data, some cross-section and so on. And these are, they will parameterize the possible self-couplings of my external particles. So when I write down lambda phi to the 4, like g, d phi to the 4, etc., it's a fit to measuring these coefficients. So these are, because of this, we call this the EFT expansion, some effective field theory. But then, as I crank up the energies and so on, I might discover new states and want to incorporate them. So then the other thing that can happen is you can produce a new state. But even though you would think, wow, there's all sorts of 3-point couplings that I can put here and here, make life completely miserable for you, the person that computes the amplitude. Again, I have symmetry. The 3-point amplitudes on shell are all unique. So no matter what cubic vertex you write here and here, it's always equivalent to the simplest possible cubic vertex on the left and on the right, plus context terms. Not only that, we can pin down the structure of the exchange amplitude for any mass and any spin. So there will be a coupling constant here, coupling constant here. There will be a g squared. Again, it's a consequence of locality. Then when I hit the pole, when I can put this particle on shell, because of unitarity and locality, this is the form of the amplitude. This is because the propagator goes on shell. When I go on shell and I'm sitting on the pole, I'm giving arbitrary distances for this particle to propagate. So on the pole, this amplitude must factorize. So the residue at the pole must be equal to product of 3-point scattering amplitudes on the left and on the right. And these are pinned by Poincare invariance. So you can pin down the residue, and that completely fixes all the possibilities. So this, my color coding, the m squared here is because of unitarity, because it's a unitary representation. And so this is mass m, this is mass little m, and if, just to be precise, it can have spin j, and I don't have space on the board. Times, when you get on your notebook, you add this. It's a Legendre polynomial. Spin j, I'm in 4 dimensions. 1 plus 2t, the other Mandelstam. Plus other channels, okay? Plus t and u channels. So of course, if it's completely symmetric, you can put this particle on shell also in the T and the U channels. Okay. So that's it. So you classified. You can go home and sleep happily tonight because you don't need to worry about the vastness of the space of Lagrangians. You can write down the most general 2-to-2 scattering amplitude. Your ability as a model builder will be to dial these EFT coefficients and to dial the spectroscopic data of the new states, of the new physics. In fact, there are way more. There's bounds on EFT coefficients. If you want to UV complete the theory. By the way, this makes it clear why higher spin particles are complicated. If I can only put simple poles downstairs, but at high energies, Legendre polynomial is polynomial in J. At high energies, this grows like t to the j. So once j is bigger than 1, the amplitude starts growing very fast. And this is the miracle string theory, that you have infinitely many exchanges, for example, or QCD, or you have infinitely many exchanges. So it seems that each partial wave is just trying to make the cross-section grow too fast against unitarity. But somehow the whole tower conspires and manages to give you a smooth amplitude. We still don't understand this, how this phenomenon works, just at the level of examples. So anyway, so this gives me inspiration that there should be an analogous story for the classification of cosmological correlators. I should be able to rewrite any 4-point cosmological correlator as a sum over exchanges plus sum of contact terms. And tomorrow, in the first lecture, I'll show you that we can do that. Okay? And then tomorrow, I'll show that the whole machinery relies on differential equations. So differential equations play an important role. And then I'll show you in a toy model, I'll show you how these differential equations are come about and like, why they're so important in this business. So that's it for today.
I guess we can have 5 minutes break for toilet or anything, and be back here for 20 to 12.